Okay, my friends, I wanted to do this little wrap-up video to kind of bring, revisit an idea that we've talked about multiple times over the past few weeks, actually, which is the effective sample size on confidence, margin of error, significance, however you want to kind of talk about it. But also explore, again, mathematically why those things happen and how it kind of ties to hypothesis testing versus confidence intervals. So in the example we just looked at, we saw no statistical significance in a sample of size 28. But remember, my sample average was larger than the null hypothesis 1400. Now what I want to do is I want to look real quick, because technology allows us to do this so quickly. We could increase the sample size and watch the effect on the test statistic and the p-value. So I'm going to change the sample to 100. Now this is fiction, pure fiction. I'm going to keep the sample average and the sample standard deviation the same, and I'm going to increase the sample size to 100. Pure fiction. Most likely those things would change. But I'm focused not on the statistics right now, but the mathematics. So what happens if I change my sample size to 100? Watch that p-value. It just got smaller, and the test statistic got further away from 0. What happens if I increase the sample size to, say, 250? Watch that p-value and that test statistic. The test statistic again got further away from 0, and the p-value got smaller. Let's bump it up to, say, 2,000. Let's say I watch this for 2. Remember, this is days, right? And I mentioned when I was kind of giving you the informal talk that I effectively maintain this level of activity year-round. So 2,000 days of this activity is not that hard to believe. What would happen? And all of a sudden, if you see it over 2,000 days, all of a sudden, what's it, about 7 years or so, which I've been bike commuting for, hell, almost 30. All of a sudden, at 2,000 days, the test statistic becomes 2.5 standard deviations away, eclipses the critical value of 1.64, and the p-value is now 0.68%. So, again, we knew, at least inherently, why this was going to happen. Central limit theorem says it's going to happen. But sometimes I find myself saying, oh, it's a central limit theorem. Let's get into the actual test statistic math just briefly and show you how that central limit theorem is kicking in. Okay, my dear friends. Now, we're going to do a little bit of math here. Don't be afraid. Don't be afraid. It's okay. It's all good. I want to make sure you buy that test statistic that's showing up in that Excel calculator, because it's important. The test statistic, which determines the p-value, gives you the level of agreement between your data and the null hypothesis. So really, that t that you see is telling you how much you can support the null, or whether you have to throw the null away and think you're somewhere else. That's important. Right? That one number is very important, and I want to look at that through the lens of something you already know. That test statistic is not just magic. It doesn't just show up. It actually throws all the way back to confidence intervals. You might have remembered back in I don't know what week it was, when we were calculating what are called t intervals, which are the confidence intervals for a population average. The t that you were using back then as the confidence multiplier, that's the same t that's here. It's just the t here is being used as a significance indicator. Potato, potato. Confidence traps a confidence interval. Significance says, okay, how different are my results from the null? Same basic idea. It's just, are you in the interval or are you out of the interval? So what we're going to look at now is how we can bridge that gap with this interval. So this is old school. You've seen this before already. This was a couple weeks ago. It's a compound inequality, which is a pain in the butt to deal with. But we don't have to deal with the whole thing. Both sides, mathematically, in this case, tell us the same thing. So I'm going to take away half of it and only focus on the left-hand side. And actually, I'm not even going to focus on the inequality. I'm going to make it equals. Because in a hypothesis test, remember the critical value? You're looking for a line in the sand, which tells us that based on a certain sample's results, which generates a standard error's results, that it's going to carry a certain t-value. Where is that compared to the line in the sand? That's what this is going to help us do. So our job now is to solve this equation for t, which is the test statistic. So a little bit of algebra here. You've got x bar minus t times the standard error equals mu. Okay, so here we go. Ready for this? I want to get t on one side by itself. I think what I'm going to do first is, I'm going to leave this whole thing here. I'm going to move this guy over here. So you're going to have negative t times the standard error equals mu minus x bar. Okay, so far so good. I hate the fact that that's negative over there. So I'm going to divide by the standard error, but by the negative standard error. Okay, the negative standard error. That'll make this side positive t. Now, since you're dividing by a negative, this is where the algebra gets a little bit tricky. This becomes negative, this becomes positive. So it's going to be x bar minus mu over the standard error. Now, dear friends, that is what you see in the Excel calculator. When you see test statistic, number of standard deviations away, this is what you're looking at. If you click in that cell, you'll see the formula. I've got it right here. The only difference is I've got the standard error actually coded. There's no standard error command in Excel. So what I have to do in Excel is I have to put the sample average, x bar, the population mu. Remember, this is the null hypothesis. This is the null hypothesis value you're testing against. So the sample average minus assumed population average. That's going to be a difference. How different? Well, the difference is going to be governed by the sample standard deviation and the square root of the sample size. And the square root of the sample size. Now, here's where the math gets fun. Remember how we kept changing the sample size? We kept increasing it. And as we increased it, the t kept getting further and further away from zero, more and more positive. Track with y. Track this with y. As n gets bigger, the square root of n also gets bigger, just not as fast, but it does get bigger. Okay, so this part of this bottom fraction is getting bigger. Well, if the denominator of this fraction is getting bigger, that means this whole fraction, therefore, is getting smaller. Good so far? Hopefully. So now this guy down here is getting smaller. So now you've got a large fraction, which is the test statistic. This part, when I was changing the sample size, this part wasn't changing. I kept the sample average. I kept the assumed hypothesis. I also kept the same sample standard deviation. So the only thing really changing in that calculation was the sample size. As this fraction gets smaller, you're making this fraction have a smaller and smaller denominator. Think about what happens as the denominator of a fraction gets smaller and smaller and smaller. 1 over 100. And then go to 1 in 50, and then go to 1 in 10, and then go to 1 in 2. What's happening as the denominator is getting smaller? The fractions themselves are getting bigger. 0.01, 0.02, 0.1, 0.5. Let's say you go past 1 over 2 and go 1 out of 1.5. That's going to be 0.666666. But it got larger. So as the denominator here gets smaller, this entire fraction gets larger, which is why as we increase the sample size here, which made this whole thing smaller, this whole thing kept getting larger. And as that gets larger, it gets further away from zero. And as it gets further away from zero, the p-value gets smaller. So that's a little mathematical exploration. That being said, I want to reiterate what I said last playlist, I guess. Just because you have statistical significance, which you saw what I did, eventually I played with the sample size enough so that I forced the p-value to be statistically significant. That doesn't mean it's practically significant. At the end of the day, my sample average is 1,429 calories. I can show that it's statistically significant if I get data with a large enough sample size to push that p-value past 5%. But is 30 calories actually practically significant? I'm going to go ahead and hazard a guess that I'm going to proofread when I'm editing this video that I probably burned 30 calories making this video right here. But that's neither here nor there. The idea is there's a mathematical reason why that test statistic looks like it does. And it looks exactly the same for sample proportions. It looks like this right here. Same exact derivation you would do here, except you'll notice the variables match the proportion and not the mean. Okay, just didn't want you to think that those test statistics were magical. They do have a point. I'm never going to make you calculate one because it's 2024 as I record this video and nobody does that stuff by hand. But I wanted you to make sure that I never want you to think that math is magical or statistics is magical. There's reasons for all the things we do. All right. Let's try the homework.